then I'll do a brief case study at the end on one of my side projects for battery recycling, and show how I use some of those techniques in my work. So in inorganic material science, we know we look at mostly bulk structures. So this is in contrast to people who work on polymers or other chemists who are looking more at molecules rather than bulk structures. But we look at crystal structures, and it's really important to figure out, or the properties of a material are very related to the symmetry and atom positions in this bulk lattice. So the classic example is the difference between graphite and diamond, where both of those materials are only made out of carbon atoms, but they have drastically different properties. And a lot of that can be attributed to the crystal structure. So for a lot of different applications, we use X-ray diffraction to determine the crystal structure of a material. So on the left, I've got an early single crystal diffraction pattern. And yeah, so a diffraction pattern from a pretty large single crystal material. Whereas on the right, I'm showing a laboratory source powder X-ray diffraction pattern. And I think I would call that the most common X-ray diffraction experiment that we do in material science. So for anyone who does synthesis, they're trying to figure out how pure the material they made is, or if they have impurity phases. You can figure out what your secondary phases in a material are by looking at the X-ray diffraction pattern. And you can do this experiment in less than 10 minutes. So we do it all the time. And in a powder XRD pattern, we're looking at the x-axis is the angle, and the y-axis is intensity. And so different crystal structures are characterized by where peaks are located and the intensity of those peaks. Things that traditional X-ray diffraction cannot tell us about is primarily local structure. And what I mean by that is crystal defects. Like in the image on the left, there's a point defect where there's one atom in the regular lattice has been replaced by some. So this is the salt crystal structure for sodium chloride. Maybe it's just some other atom on one of those atomic positions instead. We can't really see that with X-ray diffraction. Or we can't quantify it with X-ray diffraction. Same with something like on the right, vacancy clustering, or so disordered or amorphous materials, or crystal structures where the particles are too small. All of those scenarios lead more to something called diffuse scattering, which is scattering where we don't get peaks arranged into those really nice, I guess, yeah, data is not arranged into those really nice peaks. And instead we get wider peaks that are over a broader range of angles, so it's harder to quantify the diffuse scattering. So there are other techniques to look at amorphous things, for example. But X-ray diffraction, or XRD, is best at characterizing a bulk ordered lattice. So I'll use the example of graphite again. One thing that describes the symmetry of a crystal structure is the d-spacing between different atom planes. So in this example of graphite, you can see that in the same regular lattice, there are different ways we can draw a line between symmetrically equivalent planes of atoms. Whereas these two planes that are shown in the two examples on the screen, the spacing between those planes is different. And because the spacing is different, we see intensity from X-rays reflecting off of those planes appear at different angles in the X-ray diffraction pattern. And a lot of this is described, or all of this is described by the Bragg law, which characterizes which angles you would get from which d-spacings in a crystal structure. So while this equation is fairly simple, it took me a long time to wrap my head around it, with lots of diagrams and understanding triangle math. But it's the basic idea here is that we're shooting our incident X-ray beam. So I'm looking at the image on the left here. I'm not sure if you can see my mouse, but these waves coming in are our X-rays from our X-ray source. They have a wavelength of lambda, and the X-ray wave on the top is bouncing off of the top layer of atoms in this crystal structure, and the other one is bouncing off of one layer down, but the same, they're parallel planes, so they're symmetrically equivalent in the crystal structure. And in the example on the left, the extra distance that the bottom beam goes, which is the addition of this red and green part, is a integer number of the wavelength. And so what that means is that the two reflected beams constructively interfere. So they're still perfectly aligned. So we get some intensity measured at the detector from atom planes that are this d-spacing apart. So that is sort of described by the n here. The n in the equation in the Bragg law is some integer, which describes how many planes apart the reflections are adding up from. So in contrast, the image on the right is showing a scenario when you do not get a Bragg peak. And that's because the two different beams coming in, the difference in distance between the top beam and the bottom beam is not an integer wavelength. And so that means that the wave destructively interferes. And so the intensity that you get at this angle, incident angle, there's nothing there. So when you're looking at a bulk crystal structure, you're looking at many planes of atoms. And so even if at one location, you can get destructive interference from a lot of different interactions, and you can only get constructive interference in very specific situations, and that's where we get a peak. So anyway, the Bragg law looks simple, but yeah, took a long time for me to wrap my head around, and we can totally come back to this later in the talk. But I'll go into another example here with the diamond structure. So the diamond structure is actually highly symmetric. So there are only a few distinct planes of atoms in the structure. So I'm showing essentially 4 different slices through this unit cell, the diamond unit cell, which is shown at the top here. And each of these planes is a different spacing apart from each other, which means that from each of these planes of atoms, we get a different peak at a different location. So 4 planes for 4 different peaks. And the larger the d spacing is between those planes, the lower angle peaks we see. And in a powder diffraction sample, this is one thing that is also distinct from a single crystal experiment. In a powder sample, we're assuming that we have all of these little particles of the same type of crystal, but they're randomly oriented with respect to each other. So we don't have to shoot our X-ray beam from a bunch of different angles to characterize the symmetry of the system when all the crystals themselves are randomly oriented with respect to each other. So in a powder X-ray diffraction experiment, we shoot the beam on one plane, and we only have to move the detector along one axis to catch all the diffracted beams. Whereas in a single crystal experiment, you sort of set up your crystal, you put it on a little, like the tip of a needle or something, and then you shoot the incoming beam at it from all different directions, and the experiment takes a lot longer. When the particles are not truly randomly oriented with respect to each other, we see something called preferred orientation, or that is called preferred orientation. Maybe your particles are all like longer in one direction than another, and so they sort of stack up in a certain way. This would show up in your X-ray diffraction pattern by showing you different intensities. So sometimes we spin the sample stage so that we try to get rid of some of that preferred orientation showing up in our X-ray diffraction data. So far, we've talked about the main thing that we can get from X-ray diffraction, the different crystal structure phases. We can get some information from the more diffuse elements of the diffraction pattern. So, or elements of diffuse diffraction, which I talked about, were mostly related to different defects in the crystal structure. One thing is you can estimate the size of the smallest crystalline domain, because the smaller the particles, the larger the line widths from the peaks you get are. So in contrast, the larger and more perfect a crystal structure you have, the taller and more distinct peaks you would get. So the Schur equation is something that will help you estimate the smallest crystallite size. And in this case, the average size of the ordered crystalline domains is something that can be slightly smaller than the grain size, which is or something that can also be smaller or equal to the size of your particles. So a lot of time people say this equation is for determining particle size, but really you're looking at the smallest ordered crystalline domain, which could be smaller than the particle size. Anyway, there are better ways to figure out your particle size. At UCSB,
Becca?
Yeah.
On the last one, yes. Can you talk about why smaller particles give larger line widths?
Sure. The way that I mostly think about this is from or I rationalize this by thinking about the diffuse scattering, because there are so when you have smaller particles, you also have more surfaces and just more areas that are not reflecting in your ordered planes. So, man, I would have to go back to some of my other pictures, but when I was talking about the Bragg law, we're talking about how you have a bunch of planes that are separated by the same d spacing, and in a perfect lattice, that would be, we estimate that as infinite. And if you have enough of those planes, then even when the difference between the path that the incoming beam comes in on and one reflecting off of a lower plane, if that is just slightly off from an integer of the wavelength, then you would get destructive interference somewhere, because you have so many different planes. If it's shifted a little bit, you'll have one that is completely destructively interfered. If you don't have enough planes, then you might have something that's a slightly different d spacing, where the intensity is not fully canceled out by a reflection off of another plane, and so the same peak shows up as broader. This is hard for me to explain with just waving my hands around, but in general, smaller particles, more surface area, more defects, more diffuse scattering, rather than Bragg scattering, which is at a distinct angle for every d spacing. So that's the way I think about it. We can come back to that as well. Elias, thank you for your question.
No, that's a good explanation. Thank you.
Great. But yeah, like I said at the beginning of the talk, lab X-ray diffraction is something that material scientists, especially people who work on inorganic materials like me and Elias, we use X-ray diffraction all the time, especially if we're doing any synthesis and want to figure out what we've actually made. So this is a picture of the panellitical Empyrean, which is the diffractometer that we use, sitting in Ealing's Hall. And I'm showing a a picture of the geometry on the top right, which is when you're doing your sample preparation, you sort of put this flat dish where the blue is. And then the incident X-rays scatter off of your sample, and then you have a detector that moves around on this side and catches all the scattered beams at different angles to characterize your material. This reflection geometry is the most common, but there's some ways you can set it up to do other things. We use this for powder samples, but also sorry, now there's a dude with a leaf blower outside my window. Hopefully you can still hear. I only do powder samples because I do a lot of solid state chemistry for my synthesis of my materials, but I do have some friends who grow thin films or have a material that they've annealed for a while, and what they get from that is a polycrystalline film. And for this experiment to work, we only need to have randomly oriented different crystallites, which you can get if they're separate particles, or you can get them in the same film if different domains are pointing different ways. So some people work on thin films and use this equipment as well. The resolution, so the quality of the data that we can get from lab XRD, is limited by the energy of the X-ray source. For this diffractometer, it's a copper X-ray source. It has a wavelength of about 1.54 angstroms. It's important that it's angstroms because your beam wavelength has got to be smaller than the distance between most of the atoms in your plane, between the plane spacing. Anyway, if you want to get really high quality, even higher quality structure data, you need a source which is a lot higher energy. So we often send samples to a synchrotron, which is, I'm showing a picture of the advanced photon source, which is a part of Argonne National Lab in Illinois, outside of Chicago. And through some science that I don't understand, they take these X-ray beams, but bend them with magnets and send them around in circles many times so they can get going really fast. They're really high energy X-rays that are produced. So with really high energy X-rays, that means our wavelength is smaller. We're using the same principles of Bragg diffraction, but with a smaller wavelength, you can get better structural resolution. And the other thing is they're greater flux, so there's just a larger number of X-rays coming in at once. You can do these experiments really quickly. So my group uses the sample mail-in program to this beamline quite regularly. So this is a national lab that's funded by the US Department of Energy, meaning that you can apply for either time to physically be at the beamline, or like what I do so far is apply for samples for mail-in, and then you send them and they run them. The entire thing is free for the scientist, funded by your tax dollars. And you get really high quality data where it's pretty exciting that we're able to use a resource like this. And the sample prep is a little different than for that reflection geometry that we use just in the lab. This is a picture of the mail-in kit that you would get from Argonne National Lab, and it has these capped on. This is a type of polymer tubes that you stick your powdered material into this tube and cap both ends, and then they've got this magnetic sample base that you stick it in one side. There's a barcode on it so that they don't lose which sample is yours. And then at the actual beamline, the geometry they use is a little different. Instead of reflection, it's called transmission geometry. And that means you get incident X-rays here from your high energy beam. They go through your sample, which is this capped on capillary tube, and then the detector catches the scattered beams from this. So one thing that this means is you can get a much broader range of angles covered by this. With the flat stage, we're limited. Our powders are suspended there. we can't flip it upside down or anything like that. You're limited to 180 degrees around. Whereas here, the X-ray detector can be everywhere that the incident beam is not. So you get almost 360 if you want. Another thing is the sample stage spins. So I guess that's something you can do on our lab one as well. But the advantage of a spinning sample stage is you can eliminate some of the preferred orientation that comes from having particles that are aligned in a certain way. So your intensity is a little more characteristic of the unit cell. And another thing you can do is measure diffraction at different temperatures here with a special request. So you could even make a phase diagram with your same material, or I guess you could get one line in a phase diagram which says at this composition, you can measure the phase of the material that you get at a bunch of different temperatures. Anyway, here is an example of comparing a material that I made. This is molybdenum oxide, MO4O11, and it's the same material in the top image. This is lab XRD that I collected at UCSB, and then the same material sent to the beamline 11BM, which is the one that does the mail-in program at the Advanced Photon Source. And I kind of wanted the difference between these to be a little more dramatic, but the material is quite crystalline, so that's one reason you don't see a bigger difference. But the data from 11BM is a lot higher quality, and I was able to do a much more careful refinement of the data. So when I say I'm doing a refinement, it means that this blue line here is essentially the predicted crystal structure from a model structure that I put into my software. And so the gray line at the bottom is showing the difference between the structure that I'm feeding into the model and the data that I actually got, which are those little black dots. So the easiest thing to feed into your model to start is a structure file of the material that you want. But then if you have really high quality data, like from a beamline, you can tweak things like the exact atomic positions. Maybe they're shifted a little bit, or the atoms move around when they're experiencing any form of temperature. And so in different crystal structures, you'll get atom motion in different directions. And you can actually see that in the synchrotron data, which shows up as different peaks being different heights. So you can refine on everything from the crystal symmetry, the atom positions, the amount they vibrate in different directions, the crystal size, and you can make a much more perfect model using the synchrotron data. So that's why I'm so proud of this bottom one. I needed some help to get it to this point, but it's looking pretty good. And the picture on the right is the unit cell of this material, so fairly complicated. I'm not going to go into this because this is a scary equation, but this is sort of like what the software that I use. This is the Rietveld equation, and it's describing why IC is the intensity that you would get at a certain angle. And it's sort of showing you all of the different things in the crystal structure or sample that would give you a different intensity at different points. And this is the equation that the software I use is fitting behind the scenes. So luckily, I don't have to actually do this math every day. We have scientific tools. Another thing I wanted to talk about is neutron diffraction. So I've tried to be careful about saying for all the X-ray diffraction experiments, we are characterizing the structure, but there are situations where you might have the same structure of a material with different atoms on the positions in the structure. So for example, any FCC, face-centered cubic metal, but if you have copper or cobalt on the lattice positions, you still see the same structure. And the difference that you get from X-rays with different atoms is quite small. Sometimes you can't trust that in your refinement you're looking at copper or cobalt. So one way that you can actually decipher that is with neutron diffraction. So the reason for this is in this image, I'm showing the relative scattering cross sections. This is sort of like the intensity that you would get shooting each of these elements with X-rays. And the atomic number is increasing at the bottom axis. So the X-rays in all the other experiments I've been talking about interact mostly with the electron cloud surrounding each atom. So pretty much the higher atomic number you get, the more electrons you get, and the more the X-rays scatter off of that element. But that means that if you have two very similar atoms, but different atoms that are in the same crystal structure, it's really hard to tell apart with X-rays because you get almost the same scattering off of each of those. So in neutrons are interacting directly with the nucleus of the atom. So you get, there's a lot smaller difference between the nucleus of two neighboring atoms compared to the electron cloud. So it sort of evens the playing field here. And the bottom graph is showing the different scattering cross section that you would get from neighboring elements, and it's a lot more similar. This means it's easier for us to see lighter elements. Like I mentioned, I work on lithium ion batteries. You would never be able to tell where lithium is with an X-ray diffraction experiment, even synchrotron. But you can with neutrons. You can see lithium, and you can more readily tell the difference between something like cobalt, manganese, and nickel, which might all be in the same crystal structure in the cathode of a battery. So I'll go into this a little more when I talk about battery recycling, but neutron experiments can be very helpful as well. This is a Rietveld refinement. I stole this image from someone else. This was a slide that I got from my advisor, but this was the neutron refinement that he was most proud of doing. And you can get just really good structure refinement off of neutron data. This is the same sort of Rietveld refinement, but with data where you're more sure about the position of the nuclei. So on the right is this complicated structure that that this refinement led to. And you can also see that it's been represented with, instead of spherical atoms, they're sort of ellipsoids, and that is describing the different directions that the atom might be vibrating at increased temperatures, things like that. So you can get a lot of information from this. The experiment is trickier. For the mail-in program for synchrotron, I showed you those little tapped on tubes, and you can pull off this experiment with only a few milligrams of material. Excuse me. Whereas for neutron diffraction, you need a lot more material. So in contrast, so yeah, few milligrams for synchrotron, whereas if you're doing a neutron experiment, you need to send grams of material, which maybe in some fields is fine. Maybe you make a whole bunch of material at once. Me, I mostly make like up to 200 milligrams of material at once, so I could do a larger batch. But for battery experiments, sometimes we cycle a material in a battery, like stuff lithium in there, and then want to see how the structure has changed. Ooh, I've been talking for too long. And to do that, you would need to cycle the material in a battery and then harvest the material after, and then save that sample to send to neutron diffraction. But we just can't cycle grams of material at once with the batteries that we have in lab. There's so little. So you would need to do a bunch of batteries, have them all cycle the same way, and then collect that material to send it to a neutron. So that's just why it's a little less common for us to do neutron diffraction. But when we can do it, it's rad. So I'm going to briefly go into a case study here.
Becca,
yeah.
Just a quick question. Can you talk about why there's such a difference between the amount of material needed in both instances?
I wish I knew more about this. I'm not sure I know enough to guess right now.
Okay.
We can come back to it.
Well,
Do
so,
you know?
yeah.
Go for it.
You're dealing with entirely different generation means. So
Yeah,
in the first
they're a
instance,
lot bigger.
exactly. Like Becca was saying with respect to how the X-rays are generated, at a synchrotron, you're accelerating electrons around a ring. And basically, the amount of electrons that you accelerate around is going to give you the amount of X-rays that you end up generating, because just by bending them through a magnet, you get to generate some photons. In this instance, you actually, to do neutron diffraction, you need a nuclear reactor. You need a nuclear reactor to be able to generate neutrons and generate basically neutrons of a very precise wavelength in the process, which is in your process of generating those neutrons in the nuclear reactor, you're not going to be able to generate as many neutrons as the X-rays that you generate at the synchrotron. So basically, that's also part of the reason why it's a lot harder to do neutron diffraction, is because it's not as easy to build a synchrotron, or it's not as easy to build a nuclear reactor as it is to build a synchrotron. Neither is easy, but one is less easy than the other, and more risky. So that's part of the reason why. But as Rebecca has been saying, these neutrons offer a very complementary piece of information. So doing work with neutrons is very much complementary to the X-rays.
So what I'm hearing is the difference between the reason you need different sample amounts is sort of about the flux of the incoming beam.
Exactly. Exactly.
Great. Which makes sense. So yeah, there still are mail-in programs for neutron stuff, but it's a lot harder. The one I've used is at Oak Ridge National Lab in Tennessee. Yeah, if you put it in the middle of nowhere, that's usually where you find nuclear reactors. So, yeah, so I'll talk a little bit about battery recycling now and how I use these different techniques to look at this project. It will be brief, but when it comes to battery recycling, I guess general battery recycling, lead acid batteries are actually recycled quite often, but or regularly. It's an easy process. There are not too many elements in there. But lithium ion batteries are a lot more complicated. But we are starting to use them for way more things in the world. And as we make more and more electric cars with using lithium ion batteries for the energy storage there, we need to start worrying about where our supplies of these weird elements are coming from. And most notably, it's lithium and cobalt that we're sort of projected to run out of. And so there's not too much battery recycling going on right now, but it's clear that it will have to ramp up in the future. In 2019, only about 5 to 7% of lithium ion batteries were even attempted to recycle. But then it's also clear that the recycling process does not get every element back. It's sort of the entire economics of it is driven by the ability to recover cobalt and nickel. But a lot of the processes we use right now to get those elements back mean that the rest of the battery is turned into like a sludge and then is, I don't know, dumped in a hole somewhere, and so we don't have to think about it. But we don't get all the elements back. Especially we don't get lithium back, which is something that could be really valuable. So I was sent a few samples of a material. They refer to it as black mass, which is the result of a certain company's battery recycling process. And to improve the recycling process, they basically asked the question, what is in these materials that we send you? We don't know. So it is not every day in material science that you actually do get to do one of these studies to find what a totally mystery material is. So the way that I started this study was first on all the samples, we do elemental analysis, and we can have some guess about what elements might be in here, just knowing that it came from some kind of lithium ion battery. I'm showing on the screen here a typical configuration for a lithium ion battery. So on the anode side, we have a copper current collector. On the cathode side, we have an aluminum current collector, and these are sheets of metals. Who knows, maybe in the processing, they peeled everything off and could recover the copper, which is fairly valuable as well. But maybe they just chopped it all up at once. Who knows what was most efficient for them. We know that the anode was probably graphite, so just layers of carbon, maybe with lithium in between. The cathode was probably a lithium nickel manganese cobalt oxide, which is this layered structure here, also with lithium between the layers. And they probably used a polymer separator of some kind. And then in the electrolyte, we can guess that there are some salts from that too, but now we have to figure out what did all these things become as we chopped up the battery and maybe heated it up, maybe blasted it with acid. Who knows what they did? So we started with elemental analysis to figure out relative amounts of these things. So we found a lot of things we expected, but also some mystery ones, like the tools that we typically use for elemental analysis. We started with X-ray fluorescence. That's something that can give you elemental compositions, but it can't see light elements very much. So we also did X-ray photoelectron spectroscopy. Then in a scanning electron microscope, you can also do some elemental analysis. It's called EDS. And then there's also inductively coupled plasma. Basically, we have a lot of different ways we can do elemental analysis, and they all sort of have their own quirks. So we can try to use that information to guess at the true composition of the material we got. But then, which would be important for figuring out, rather than just elements, actual compounds, we sent these samples to a synchrotron. So this is my best fit at the moment for what was in here. And a lot of it was fairly surprising. So things that were not surprising: graphite. There's tons of graphite in both the anode and the cathode. And let's see, we found copper from the current collector. And the other elements in here are not surprising, but the compounds they made sort of are. Like, we started out with the cobalt in a lithium cobalt oxide, and usually oxides are more stable than the constituent metal. But maybe this whole sample was heated up and it's in the presence of carbon, which is a reducing environment, rather than oxidizing, which would happen in oxygen. So it looks like we had the conditions in the recycling process to get metallic cobalt, which is something they want. We want to be able to get the cobalt out, even though it's all sort of still mushed up into this black powder. Knowing that it's here means that they can find a way to get it out of the powder. And then one thing I'm trying to see is, do we actually have lithium fluoride in here? This is a salt that might have formed. The fluoride might have come from the fluorine might have come from the polymer binder, or also the salt that's used in the electrolyte. But this is interesting to know. It's not in metallic form. Maybe we have some salt. But something that's tricky with synchrotron, and I mentioned this earlier, is cobalt and copper are both face-centered cubic metals. They have extremely similar structures. By virtue of being different sizes, sometimes the lattice parameters are a little different, but you need to be pretty sure of your refinement to confidently tell the difference between these two. So you can see that the little copper peaks here are just the same sort of pattern of peaks as we see in the cobalt, but just slightly shifted. And I assigned these to each other because, as in the cobalt could have been the copper. Maybe I switched them, but the lattice parameters were a little closer to the known lattice parameters if I assign it this way. But there's still some question. Did I get that right? There's some question of, are we seeing all the lithium? Where could that be? So the next thing we're trying is sending it to Oak Ridge National Labs. And that's how I got some neutron diffraction. We want to try and find out where the lithium is most predominantly, but we also want to say, is it cobalt that I'm seeing, or is it nickel, which is right next to cobalt? Is it actually all copper? So this is showing a fit of the same phases that I showed on the last slide. But sometimes there's a little more resolve between the locations of these peaks. And we should see a different intensity. But normally for all of these X-ray diffraction experiments, this is the most phases I have ever assigned to the same sample. So this is so complicated. There are so many different phases that we still have work to do on this fit. And you can tell that even like some of here, I have the location of the peak mostly correct. Maybe it's a little shifted, or maybe the peak shape is incorrect, which is why I get a little wiggle here instead. Or like this one appears, my calculated peak is a little to the left of the real peak. So the structure refinement is not perfect. There's more work to be done here. But it is really useful to have the complementary methods, the synchrotron and the neutron, because each of them can tell us something that the other can't. So given that we're stuck in this zone of having a really complicated bunch of phases, my next steps on this project is going to be try to mimic the original system, which was like graphite and all these oxides and different metals mixed up together. Can we take just a few of these elements, like say just the lithium cobalt oxide and the graphite together? If we put those two things through the same set of processing that the recycled material was, what phases do we get out of that? And then can we more confidently match those to the complicated material, which is like all of these mixed together. So we're still working, but in the next steps of the project, we will definitely be using both synchrotron and neutron diffraction as well. So I wanted to wrap it up here, but I'm happy to take any questions, and thanks for your attention.
Thank you, Becca. Questions?
Happy to be here. I put someone else's picture of the Bragg law here because it took me looking at a few different diagrams to really get this when I was first learning about it.
Okay. So I want to ask a question regarding basically like if I get a sample and it's just a mystery sample, like how do I go about deciding whether X-ray diffraction is for me?
Given how easy it is to do a lab XRD experiment, I would probably just say do it anyway. There's no downside. But so it's not going to help you if the material is amorphous and so it doesn't have a regular crystal lattice. But then again, you can tell that from X-ray diffraction too. You can say, wow, I didn't get any peaks. It's all, I don't know, weird large bumps. Then maybe I'm looking at a glass. But yeah, starting with, if you just try to say, look at your X-ray diffraction pattern and then ask our software to look at the entire database of XRD patterns and say which one matches, it's going to give you a lot of like truly strange matches if you don't give it some constraint of which elements could be in the sample. So if you're starting from a mystery sample, it does help to start with various techniques we have for elemental analysis to say, okay, we saw these elements in there. Now you can plug those into your software and say, hey, among these elements, which have an X-ray diffraction pattern that matches some or all of these peaks, and it might have a better guess. Does that answer your question at all?
Yeah, it does. It does.
Yeah, we have some X-ray diffraction sample holders where, and Elias has tried to work on improving this, but we both work on a lot of air sensitive materials. So we're trying to find a way. Normally during an X-ray diffraction experiment, your sample is exposed to air during the experiment. And even if it's a quick experiment, sometimes your samples take on water really quickly or oxygen. They oxidize. So Elias is working on making a better air-free holder so that we can still see what's in there without exposing samples. One of the ways that we used to do it with the capped on film, which is the same thing that those synchrotron sample tubes are made out of. But on the laboratory scale, we sort of see a larger amorphous background from that. So if you don't have a really crystalline material to begin with, the peaks might not show up above the background. So we're looking for other options.
Any other questions?
I have a quick question.
Oh, please.
I know that you're talking about how typically we use a lot of like powder XRD. Would it be possible for like hypothetically, like if we like made something into like a pellet, like could you take the XRD of like the pellet, or could you get a scan of that, or like would we have to like make that into a powder and then take the XRD of that? Like what would be the difference between the two?
That's a great question. So I've definitely seen people do this with a pellet using the same instrument. So because all we really need for this to work is that we have different particles in the material, doesn't matter if it's loose or pressed into a pellet, that are oriented differently. So one thing the pellet could do was add preferred orientation. If there's any irregularity or any non-spherical shape to your particles, by pressing it, you might make them all align more. So you'd have to be more aware that preferred orientation might be affecting your sample results. And the other thing is the height of the reflection, or sorry, the height of the sample, and therefore where the beam is reflecting off of it, can also lead to some differences in during the data analysis. Some things change. And so you would need to sort of make sure that your pellet, the surface of your pellet that you want the X-rays to reflect off of, is at the same height as the normal sample stage. So there's a way to do it. You just have to be aware of which things are different. And I think that would mostly be sample height and preferred orientation. But yeah, I think there are definitely some scenarios where you would want to keep it in a pellet.
Okay, yeah.
Most of the time I do experiments and you put it in the furnace in the form of a pellet, and mostly we just grind it up and then do XRD. It's a little easier.
Okay, thank you.
I have one more question. Could you touch briefly on the use of like in situ XRD with respect to battery science?
Sure. We're trying. So in situ or operando are both things that you would do while your battery is constructed or operating. And that's very useful for my experiments. Since I work on the electrodes of the battery, we do expect that the structure changes as you put lithium in and take it out. So a lot of the time I used to do ex situ experiments where you discharge the battery to different amounts. So you're either stuffing in lithium to different amounts, or pulling it out to different amounts. And you can control that by what voltage you discharge to. And then opening up the battery again, taking that material out, and then putting it in a tube and sending it to the synchrotron. But it takes a while to get that data. Who knows? Maybe sometime your material was air exposed. You don't figure out until 6 weeks later, and then you have to redo the experiment, and you're behind. So what Elias is talking about is, can we actually look at the structure of the material as it's still in the battery? And that's something we're working on. We're close. One problem is your battery has to be air free on the inside. So we need to somehow seal up the battery, but still have a way of shooting the X-rays in and looking at the structure of, say, your cathode. So one way that we do that is with a beryllium window. Beryllium is a material that has only a few peaks in the crystal structure, and they happen at fairly high angles. And since we know exactly what they are, we can sort of, otherwise they're transparent to X-rays. The X-rays can go through, look at your cathode material, and bounce back out. And then from the final pattern we get, it's pretty easy to subtract out the beryllium peaks, so you can see what's happening just in your material. So that's how one would do it. We're still working on fixing our operando cell here, but yes. It's pretty cool when you can leave the battery cycling when it's in the diffractometer, and we use the same powder lab XRD equipment in Ealing's, and then leave it charging and discharging, take an X-ray scan every 20 minutes, and then you can plot that all up next to the charge discharge pattern and say, wow, I got like all these peaks suddenly move to the left, or these ones disappear. And you can sometimes correlate that with maybe a certain voltage plateau that you see in the discharge. So
yeah, it's a really great way to start to learn about like solid solution behavior or actual phase transitions and how your battery is actually getting its capacity out. It's very cool. Sweet. All right. Are there any more questions? Okay, I'm going to take that as a no. Thank you so much, Becca, for this wonderful presentation.